Okay, we're now recording. Let me hit a couple of announcements first. I'll turn on the projector so it can be warming up before we get there. If you are planning to do this research experience for undergraduates, the one I've been announcing for weeks now, the deadline's today. So if you are going to do it, get it in today. Okay? So
that's what, which one?
This is the one for mechanical, electrical, materials engineering. This is one of probably several for this, but it's at University of Illinois, University of Arkansas, and Howard University. 10-week internship. It's POETS, which stands for Power Optimization of Electrothermal Systems. Okay, and the deadline they had listed for the 15th, which is Saturday, which is bizarre. The brochure said the 17th, so I'm hoping that's it. Oh, no, okay. I thought that said noon, but it said 2020. Okay, just glancing at it, I saw the 2 zeros and thought it was meant. Now here's something new. I'm just guessing that probably neither one of you want to do this specifically. However, you may know of someone who really would love to do this. Okay? This is Line Worker Training Program. This is in partnership with Alabama Power and various utility and contracting companies. And what it is trains people to be line workers for either power companies, phone companies, others, the program information is the applications are accepted through Wednesday, so this is very short notice as well, through Wednesday, the day after tomorrow, February 19th. The training duration will be from June 8th through August 14th, 2020. The class meets Monday through Friday, 8 to 4. I mean, solid. 9 weeks. What's that? 6 hours a day. I'm sure there's a break for lunch. No, I'm sorry. 8 hours a day with a break for lunch. The program tuition, $4,150 plus fees. Now, the fees include books. I don't know how much they'll be. PPE. I don't know what that means. Some sort of education credit, I don't know. CDL physical, that's commercial driver's license physical, and then permit/licensing and exam fees. So you are going to be licensed and permitted to do this, but you've got to pass the exams to do so. And you have to pay to take the exams. But the good news is scholarships are available. They must be really hurting for people going into the line worker training. So they have some money, maybe not full scholarship, maybe partial, maybe full, I don't know. But here are the program outcomes, and these sound pretty good. OSHA, which is Occupational Safety and Health Administration, maybe something like that. OSHA 10 certification. Now, of course, you have to pay to get that certification, but if you complete this course, you will be OSHA 10 certified. You will have a commercial driver's license, the CDL. And the reason is you have to be able to drive trucks like that, and that requires a commercial driver's license. You'll have some cardiopulmonary resuscitation, CPR training, and you'll have basic line worker skills. So if you are interested, maybe you're not, but someone you might know would be interested in this, contact us here at Austin State, the Office of Workforce Development, and I'm pretty sure that's right across here in Ethel Hall. If it's not, it may be over here in Millsouth Building. If not, it may be on the Birmingham East or West campus, but it's somewhere here at Austin State. Dr. James Gray is the Workforce Development Manager. I have a phone number for him. I have his email address. I'll be glad to share that with you. And Mr. Tommy Hobbs, I know his office is right over here in Ethel Hall building. He's the Associate Dean for Workforce Development. And this number that's given is a 929-3519 that typically means this campus. I'm pretty sure, because we're 3 4s and 3 5s. So I'm 3449, 3519. I'm pretty sure it would be on this campus. Can't guarantee that, but I'm pretty sure it is. And then there is a place to apply. It's eventbrite.com. It's pre-apprentice power line worker application tickets, and then other numbers and stuff with that. So if you need this for somebody you know, someone you think might be interested, please get this information because Wednesday's the deadline. So I wanted to get that said because I just printed that out this morning. I probably missed it when it first came out, but anyway. Okay. Now, any questions on anything we've done so far? Last Wednesday, it was just me and me alone. So I recorded the class. I don't know if you followed it, but if you did, that's where we're going to pick up now. And this is in Chapter 2, First Order Differential Equations. 2.3 is talking about linear equations, and we've talked about what constitutes a linear equation. Here is how you go about solving linear first-order differential equations. This is on page 56, the bottom half of the page. Okay? Remember to put the linear equation in standard form. Whoops, let me get my pen set up. Okay, and we've already talked about this, but when we get to it, I'll go back and put it down. In fact, I'll do it quickly here now. It looks something like this: dy dx plus p of xy is equal to f of x. Okay. Now, if there's a minus sign, that's okay, because just incorporate that in your p of x, okay? But that's the standard form. Now, just a quick review, what makes it a linear equation? First order, of course, means there's only a first derivative, no second, third, or fourth derivative. Linear means that the first derivative only shows up with an exponent of 1. The function y only shows up with an exponent of 1. Okay? Has to be a linear function. Could not be sine of y. Okay? Only y. Okay? Also, the term that contains y cannot contain y prime. They have to be in separate terms, separated by plus or minus sign. That's what makes it linear. Okay. Now, the p of x, that can be any function in the world. Well, almost any. Okay, f of x, any function in the world. Those are functions of x. They don't have to be linear. That's not the point. It's linear in y. Okay, so there's the first. The second, you get it in standard form. Oh, and part of the other thing in standard form, notice the derivative term is only coefficient can be the number 1, okay? No other numbers, no other variables, okay? No x's in there. Get it in standard form. Number 2, from the standard form, identify the p of x. Now, it may have a minus sign in it. If this is a minus, incorporate the minus in the p of x, okay? And once you found p of x, then you integrate the p of x dx. Now, when you integrate that p of x dx, don't put a plus c. We'll do that later. So it's just this. And once you get that integral, then take the e of that integral, okay? So whatever function that turns out to be, make that the argument of e. I would have done that in 2 steps. They did it in 1. Okay? No constant needs to be done with integrating. Okay. In fact, I'm going to back off here. I'm going to change from what they do. First, you do that, and then I'm going to change the number. Then, whatever that function that turns out to be, make that the argument of E. It's 2 separate steps. Okay. Then what they list as 3, I'm listing as 4. Multiply both sides of the standard form equation by the integrating factor. This, by the way, is your integrating factor. Okay? Okay? So you have your equation there. Your standard form of the equation, multiply this E to that thing. Now, okay, catch this, okay? You're actually going to integrate that first thing in step 2. It's just going to be a function, okay? And then E to that function. You're not going to have the integral there anymore, but whatever that function is E to that, okay? So this looks more complicated than it really is. So this thing, E to that thing, is the integrating factor, multiply both sides, every term on both sides of the standard form, okay, equation, by the integrating factor, that's this one right up here, okay? Now, point. Now the left-hand side should be, it will be automatically the derivative of the product of the integrating equation and y. Now I'm going to shorten this integrating factor to IF. That's the integrating factor. I'm just tired of writing it, okay? Okay. It will be. Always check and make sure it is. I always do, just to make sure I haven't skipped something, messed something up. Okay? And this is how it looks, but it's never this complicated looking. D by dx of the integrating factor e to the integral of p of x dx. That's the integrating factor. Whoops. Times y is equal to this e to the integrating factor times your f of, f of x. Okay. 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 That is a perfect derivative of a product. Okay? Now, since that's the case, then what you do is integrate both of these by dx. This is step 5. They're calling it 4, I'm calling it 5. Integrate both sides and solve for y. Okay? Now, this is just going to give you you see, the integral of a derivative is just going to be the argument. So this is going to give you e to the integral p of x dx times y is equal to the integral of e to the integral p of x dx times f of x dx. Okay? Now, what you'll do then, of course, is whatever this is evaluated, you're going to divide it out. So don't sweat that. We'll get there in a minute. Okay? But this is actually much more wordy and difficult to follow than if you just do it. So let's just do it. So, all right, to erase. All right. Let's solve this one. This is example 1, very bottom of page 56, moving to the top of 57. Solve this. dy dx minus 3y is equal to 0. Now, before we do anything else, this could be done by separation of variables, and it's very easy. Let's do it by integrating by linear. Okay, number 1. Is this a linear function, a linear differential equation? Yes, it is. It's first order, dy dx, and y is just to the first power. This is to the first power. There's your coefficient of -3. So the p of x is going to be -3. And your f of x is 0. Yes, that's linear. Okay. Coefficient of dy dx is 1. So it fits the bill. So the first thing you do, identify your p of x. P of x is equal to -3. That's it. That's it. What you do with the p of x? You integrate it with dx. Well, since it's a constant, we just integrate dx. Now, if there was an x in there, we'd include that in the integral. But we don't need to. It's just a constant. So this is equal to what? -3x. That's it. Don't do a plus c. We don't need it now. Okay? Just that. Okay? Then what do we do once we found what the integral of that is? Make the argument of e to the x. So your integrating factor, and here again, integrating factor, that's not if, that's integrating factor, is e to the -3x. Okay? So what we're going to do, now multiply that by every term on both sides. E to the -3x dy dx minus 3 e to the -3x is equal to 0. Because e to the -3x times 0 is still 0. Okay? Now what we hope to be the case, that this is the perfect derivative of d by dx of e to the -3x times y. The question is it? Well, that's a product, right? So the derivative of the product would be derivative of this. Okay, first times derivative of the first times the second plus the second times derivative of the first. Derivative of the first times the second plus the first times derivative of the second. Well, let's do the first time derivative of the second first. E to the 3 minus 3x dy. That's it. That's it. The other one is derivative of this times that. Well, derivative of this is minus 3 e to the minus 3x. There it is. And derivative that times y. I think I left off my y. I did. I did leave off my y. See, I did make a dumb mistake there. Okay? Because it was, we multiplied this integrating factor by this, and I should have multiplied it by that. I meant to put the y in there. I forgot. So yeah, that is a perfect derivative of it. Well, if that's the case, then this is d of e to the minus 3x y equal 0 dx. Okay? This is sort of dumb to write it that way, but I'm going to. If you integrate this, you get e to the minus 3xy, because the integral of a perfect derivative is whatever is inside there, okay, is equal, and what's the integral of 0? A constant, exactly, okay? There is your constant. Now solve for y. Multiply both sides of the equation by e to the 3x. And this becomes 1, right? E to the 3x over e to the 3x is 1. So there's your equation. Y of x is equal to c e to the 3x. Okay. Like we said, you could have done this. dy dx is equal to 3y. Just add 3y to both sides, right? And now you can solve this by separation of variables. dy over y is equal to 3 dx, right? And integrate both sides. What does this give you? Natural log of y is equal to 3x. And now e both sides. Oh, plus c. Okay? So this is y is equal to e to the 3x times e to the c, which we're just going to call c. Yeah, there's your answer. Both the same way. So yeah, that one could have been worked. Separation of variable, piece of cake. It works this way too, and it comes out correctly. So we're happy. Happy, happy campers. Okay. And where is this good? For all values of x. From negative infinity to positive infinity. There's no limitation. Okay, with that, ready to go to example 2? Okay. Solve this. dy dx minus 3x, minus 3y is equal to 6. That's looking a lot like the last one, isn't it? Only difference is we've got a 6 rather than a 0. So do you think you can solve this by separation of variables? In effect, you can. It might be just a little rougher going than the last one, because that was so easy. But you can still do it, because your right-hand side would be, you have equals 6 plus 3y, and that is a function of y alone. Then you divide that and do the other. And it will work, but excuse me, it'll be more work. But let's do it this way. Guess what? Everything starts off the same, right? What's the first step? Figure out what your p of x is, and what is it? Negative 3. And then you do what to it? Integrate that dx. Okay? So that becomes minus 3x. Okay, don't add a constant to it, just minus 3x. And what do you do with that? Same as before, you e it. Okay, I'm sorry, that's not the best terminology. Make that the argument of the exponential function. So your integrating factor is e to the minus 3x. Okay, now you take that integrating factor and multiply it by both sides. E to minus 3x. I'm just going to put y prime. I'm tired of writing dy dx. Minus 3 e to the minus 3x d is equal to 6 e to the minus 3x. Okay. Hunky-dory? Okay. Now, hopefully the right-hand side is going to be the perfect derivative of your integrating factor e to the minus 3x times y. This should be equal to e to the 6 e to the minus 3x. Okay? Let's see if it indeed is. First we'll have e to the minus 3x y prime, first times the derivative of the second, plus second times the derivative of the first, y times minus 3. I can't get the pen to pick up. Come on. There we go. Plus, well, it is a minus. Plus a negative. Okay. Minus 3 e to the minus 3x y prime. And sure enough, that is indeed what we've got there. Okay, just verifying that, I'm going to erase it. Just want to make sure I hadn't made a dumb mistake somewhere. So this is d of e to the minus 3x y is equal to six e to the minus 3x, and my pen sat down for a second there and drew a line, dx. I knew there was something I was leaving off there. I moved the d, wrote it in differential form. Well, the integral of a perfect derivative is, indeed, whatever the inside is. Okay, so this is e to the minus 3x y is equal to 6. What's the antiderivative of e to the minus 3x? Negative 1/3. Perfect. I'm going to put the minus here, put the 3 down here, e to the minus 3x, right? Plus c. And we'll fiddle out with the c later, okay? So this becomes a minus 2e to the minus 3x plus c. Excuse me. Let's multiply both sides of this equation by e to the 3x. That will wipe out this, and that will be times e to the 3x. It'll wipe out that, and this will be times e to the 3x. And we aren't sure what it's going to do there, but let's deal with it. Here, everything goes except the y. So you got y is equal to minus 2 e to the minus 3 let's see where to put this constant. Okay, this one obviously goes to 1, so let's just take that out. Okay. Sorry, my throat's clogging up on me. These two go to 1, so that's minus 2 plus c e to the 3x. I think that may be about as simple a form as we could do it. No, I'm sorry. Minus 2 plus CE to 3x. That's exactly right. And again, your interval is minus infinity. Yeah, that's ugly. Yeah. All real values of x. Okay. Now, I said we could do this by separation of variables. And I think, well, I know you can. I was just going to see if it's worthwhile to do so. Well, they don't even mess with this. They go back and say this is an autonomous differential equation because you can write it dy dx is equal to 6 plus 3y. And then eyes of water. This weekend we were burning a lot of brush and shrubs and things like this. You know, junk that was flying around. And I got smoke in my eyes, I got smoke up my nose and stuff, so I've been coughing, sneezing, and now my eyes have just started burning. I hope it's left over from yesterday and not something else. I feel like they're watering on me. Does it look like that thing is sort of strobing a little? Okay, good. I was hoping that wasn't my eyes, because if that was my eyes, I probably had a migraine coming on. I don't want that. So I'm glad that is really that and not me, because enough other weird things is happening. In an autonomous differential equation, what you would do is dy dx is equal to 6 plus 3y. Just add that to the other side. And where that's equal to 0, that's going to be your horizontal asymptote, right? So that's 0 at y is equal to 6 plus 3y. Set that equal to 0, and you have 3y is equal to minus 6. So y is equal to minus 2. That's minus 2. And then you have your equations coming down, approaching that horizontal asymptote. Okay? And they show you in the book what that would look like. And again, they call this the equilibrium position. -2 is the critical point. And they say it's unstable, and it's repeller. We talked about that before. But what that means is coming from the left is stable, going to the right it gets unstable really quickly, because that's e to the 3x. If that had been a minus 3x, and it's been coming down like this or up like this, and becoming stable. That becomes unstable as time goes on. Now, the next thing we talk about here is this thing about a general solution. And basically if you have And they're going back to this really complicated looking form here, which is basically, I got you this far last time, so that you could divide by this, which is the same as multiplying by e to the minus that, your integrating factor. And that's a really complicated looking form here. And what they're saying here, if your differential equation is of a linear form, then you should get an answer that's of this form, which is anything but linear. I mean, it's really somewhat complex. But it's also saying if you can come up with an equation that looks like this, it has to come from that linear equation. If you have an initial value, then otherwise with the C in there, you have a different number of solutions. Pick a C and you have a different solution. Pick another C, a different solution. But if you have an initial value, then plug in the x is 0, y is 0, and solve for that C, and you get the specific, the general solution. Okay. Now we're not going to do initial value yet on example 3, but it's going to lead you up to that. So this is a little more complicated example than the first two have been. I would say a lot more. Okay? All right, to erase? So here's example 3. Yeah, and it starts off with another step. X dy dx minus 4y is equal to x to the 6th e to the x. Okay. Is that a linear equation? Second? It is a linear equation. Is it in standard form? Why not? Because what? What coefficient? Okay, say that one more time. This right here. Is that what you mean? Yes. This should not be here. For it to be in standard form, you need to divide this out. Because you want this by itself. A naked derivative there. Okay? No, nothing else. So the first step is to divide by x. Okay. Over here, they completely go and you get dy dx minus 4 over x times y is equal, this becomes x to the 5th e to the x. Is that in standard form? Yes, it is, because the coefficient here is 1. What now is your p? Negative 4 over x. Is that okay to have? That's not very linear sounding. Doesn't matter. It's only the y that needs to be linear. This is perfectly linear in dy dx and y stand by themselves, that's fine. So we named this the p of x is equal to minus 4 over x. And then what do we do with that? Integrate it. Okay, and what does that become? Natural log of x. Don't add any constants at this stage, ever. Just do that integration. I think I've got a piece of apple stuck between my teeth and it's bugging the fool out of it. So there's your integral of p of x. Now what do we do with that? Use that as the argument of e. Well, then I don't like this form. I want to change that, and using a rule of logarithms, this is the same as log of x to the minus 4. Do you remember that one? Okay. Why do I want to do that? Because before I take an e of it. What does that become? Yeah, that just becomes x to the minus 4. Why? Because a log and an e are inverse functions of each other, so the e and the log do out. So that's why I wanted to make sure the minus 4 goes up there before I take the e out. You could have waited till later, but that made it so much cleaner. This is now our integrating factor, okay? Not iffy, but if, you know. Now, what do we do with it? We multiply both sides of it by our equation, our modified equation. So this will be x to the minus 4. I'm just going to write it y prime minus 4 over x to the 5th, because that's 1 over x to the 4th, we already had this, times y is equal to x to the 5th e to the x. Yay? Oops. Times x to the minus 4, which then would make just this x e to the x. If we multiply that by x to the minus 4 times x to the 5th, you get x to the first power, right? Okay. So I'm going to erase that blob there, okay. Was a 5th, but then we added minus 4 to it and it just became a 1. Okay. Now, first, verify that this is indeed d by dx of what we have here. Your integrating factor e, it's not e. Most of the time it is e, this time it's not. It's x to the minus 4th times y. Is that indeed the case? Well, take the derivative of a product. It's the first time derivative of the second. That would be e to the minus 4th times y prime. Yes, that's right. Plus y times the derivative of this. So the derivative of this would be minus 4 x to the minus 5. Sure enough, that's what you got to get times y. So that is a perfect derivative, right? Okay, and that's equal to x e to the x, and then take our dx and move it over here, or write it in differential form, and this becomes x to the minus 4 times y, because when you integrate a perfect derivative, you just get what's on the inside, is equal to the integral of x e to the x dx. Now this is where it gets a little more interesting or a little more involved. How do we integrate that right-hand side? By parts. And what parts would you have? Let u equal which part? X, then dv is equal to e to the x dx, then du is equal to dx, and v is equal to e to the x. Ha! Done. Okay? Except, now we write uv, this integral on the right, is going to be u times v, which is x e to the x, minus the bottom line here, the integral of e to the x dx. E to the x here, dx there. And what does this give you? Yeah. X e to the x minus e to the x dx. This is x to the minus fourth times y. Now, what we have to do is put a constant in here somewhere, okay? At some point, we need a constant in there, okay? I'm sorry? Okay. Second line here, or which? Oh, here? Okay. Oh, yeah, I'm sorry. Yeah, I see what you mean. I'm sorry, I was just writing down. Yeah, we already integrated out the dx. Yeah, that's what we got. Okay? And one last step to get it explicitly for y. Multiply both sides by x to the fourth. That gives us y is equal to x to the fourth times x is x to the fifth, e to the x minus x to the fourth, e to the x plus c times x fourth. Okay. And this didn't have an initial condition, so we basically almost through. Let's see what we got. Y is equal to x to the fifth, e to the x minus x to the fourth, e to the x plus c x to the fourth. Done. Now, here's possibly a little bit of a problem. Okay? What was the first step we did? Divided by the coefficient, right? Now that obviously meant x can't be 0. Okay? Because you can't ever divide by 0. But guess what? If x was 0, then this is 0. And that is 0. And you have minus 4y is equal to 0. So y is equal to 0 is a possible solution, right? Does that show up here? Well, if x is 0, yeah, y is equal to 0 would be a solution. Now, they say it's a singular solution because that would be what you got when you divide it there, but that's included in your thing here. So I really don't see why they make sort of such a big deal about it. Except that it can't be 0. Well, I don't know. What you did to get here, you couldn't do legally, but it still gives you an answer of y is equal to 0, which seems like you're okay with it. Except, you know, you can't be 0 there if you divide it by 0 here. Yeah. So it's kind of a catch. I don't know if you actually call it a catch-22, but it's, as it said, they are potentially troublesome, and that could be. So let's see if example 4, if that's even more troublesome. So let's go to example 4. You go okay with this as written? Okay. Now, according to what I see here, we've got plenty of time left, right? Okay. We're just over halfway. Find the general solution of this one. X squared minus 9 dy dx plus xy is equal to 0. Is that a linear equation? Did I hear yes? Yeah. Is it in standard form? Why not? The x squared minus 9 is your coefficient in front. So how do we usually go about getting rid of it? dividing by x squared minus 9. So we'll divide this by x squared minus 9. And we'll divide that by x squared minus 9, which usually is basically a waste of effort because that's still 0. Okay? So now we have dy dx plus x over x squared minus 9 times y is equal to 0. Now what do we do? You said multiply it by what?
Like by itself. Like the x squared minus 1y.
Okay. That's your p of x, right? And what do we do with p of x? No, we integrate it. Remember? Integral of p of x. So we do the integral of x over x squared minus 9 dx. That's what we do with it. How do we do that? Okay, I think a substitution might be in order here. What's the substitution? U equal there are actually two ways we could do this, but we'll do it this way because you suggested it. What's your U equal? X squared minus 9. Then du is equal to 2x dx. But we don't want, we have an x dx. We don't want 2x dx, so we'll divide both sides by 2 to give us x dx. And that's du over 2. So this would be 1/2, the integral of du over u. Okay? Because your u was this, the 1/2 we get here, the 1/2 x dx is du over 2. So what does that do? How does that integrate? Natural log of u. But what is u? X squared minus 9. Which then could be written as the log of x squared minus 9 to the 1/2 power, or the square root of that, right? Okay. What do we do with that integral of p of x? That's really what we've got here. Make it the argument of e, which is a nice thing to happen because this then becomes x squared minus 9 to the 1/2 power, or the square root of that, however you want to say it. All right, then what do we do with that? That is your integrating factor. Okay? So we multiply it by things on both sides, and that gives us, I don't know how to write it. I'm going to leave it in that form, I think. X squared minus 9 to the 1/2 power dy dx is equal to, multiply it by here, and that gives you x over x squared minus 9 to the 1/2 power. Because back is itching in a spot I can't get to, and it's driving me nuts. Okay. When you multiply the square root of something here, but you have that thing here, in the denominator here, the square root goes into this square root times, okay? So that's what you get. And for some reason I'll put an equal sign there, and that is a plus sign, if I'm not mistaken. Yeah, that's a plus. Okay. And this is a y, and that's equal to 0 because that thing multiplied by 0 is still 0. So this is supposed to be d by dx of the integrating factor, which is x squared minus 9 to the 1/2 power times y. Let's see if it is. Okay. So that will be the first times the root of the second. That's exactly what we've got here. Plus the second, there we got that, times the derivative of the first. And the derivative of the first is 1/2 of this thing to the minus 1/2. That puts it there, except we have a 1/2 up front. But then chain rule in it times 2x. 2's cancel the 1/2, and that leaves you an x. Sure enough, that is a perfect derivative. Okay, and that's equal to 0. And if you were then to move your dx over here and integrate both sides, that gives you integral of a perfect derivative. Okay, it's going to be x squared minus 9 to the 1/2 times y is yuck. Okay, is equal to a constant, because the integral of 0 is a constant. Okay, and then all we have to do is y is equal to c over the square root of x squared minus 9. Okay, now that's one way to write it. You don't have to write it that way. Now, here's the place you get problems. Well, I really don't think you do. X cannot be plus or minus 3 here, right? Because that would make this 0. Those are the only values of x. Well, x can't be plus or minus 3 either, because that would make that 0. Second? Yeah, it can't be that. And x also has to be between minus 9 and 9. Not counting either one. Because, I'm sorry, I said it backwards. It has to be outside of this. Less than negative 9 or greater than positive 9. Because otherwise, this doesn't make sense. Okay? Because if x was, say, 0, you can't do that. Is that what you were saying? Yeah. And if it's 1, you can't do it. If it was 2, you can't do it. If it's 3, you still can't do it because now it becomes a 0. So it has to be less than negative 9 or greater than positive. So those are the only places that this would make sense. So you have those two intervals, and you would depend on your initial condition, if you had one, to determine which of those would be the case. So therefore, this is good only on minus infinity to minus 3, but not counting minus 3, and the interval 3 to infinity. Those are the only places that this is legitimate. Something to get to scratch that place where it itches, but that's not going to work either. All right. So it's got to be over there or over there. It can't be in between 3 or minus 3 and 3, or even 3 or minus 3. So x equal 3 or x equal minus 3 are singular points in the equation, and that every function in the general solution is discontinuous at those points. On the other hand, x equals 0 is a singular position of the differential equation in example 3, the one we did before. But the general solution is noteworthy that every function in this one parameter family is continuous at x equals 0 and therefore is defined. So that was kind of what they were talking about, those singular points. That one, it can't possibly be the one we just finished. Can't possibly be a solution. But in the one we did earlier, where x couldn't equal 0 here, it could be a solution there. So it's strange but true. But you know, we do that kind of stuff sort of frequently. How I was going to say we could solve this before I thought, and you said, of doing it by substitution, you could have done this with partial fractions. Okay? 1 over x plus 3 times 1 over plus 1 over x minus, or a over x plus 3 plus b over x minus 3, and done it that way, you'd have come out, I think, the same way. Okay. Now, any questions on those? Let's move on to example 5. Now, we got about 10 minutes left, is that right? Huh? Okay. See if we can get example 5 done. Here we have dy dx plus y is equal to x. This is an initial value problem. Y at 0 is equal to 4. All right. Now, on first glance, would you say this could be done by separation of variables? Yay or nay? No, because you'd have to subtract y from both sides, and that gives you y minus x. You'd have to have a product or quotient of x's and y's for it to be separation of variable. This doesn't fit the bill. So this is probably our only shot at this one, is linear solution. So is it a linear equation? Is it in standard form? Yes. What's the next question we ask ourselves? Do you need the p? No. What is your p of x? 1. Okay, well that's it. P of x is equal to 1. So what do we do with that p of x? We integrate it, dx. And what does that give us? X. Okay, and we don't ever do a plus c. So once we got our p of x, what do we do with that? Argument of e, so that becomes e to the x. This then is our integrating factor, e to the x. So what do we do with that integrating factor? Multiply it by both sides. So we get x dy dx, okay, plus xy is equal to x, or e to the xy. Goodness gracious. E to the x dy dx plus e to the xy equal e to the x e to the x. I can't talk. I can't even, okay. Multiply e to the x by everything on both sides. Now what we're hoping that this is perfect derivative of your integrating factor e to the x times y. Is it? Well, if you take the derivative of this, derivative of that is e to the x. Now, I'm sorry. This times the derivative of that, sure, that's what you got, plus derivative of this, which is that, times y. Yes, that is a perfect derivative. And that's equal to x e to the x. So let's get rid of the dx and move it over here, and then integrate the perfect derivative, and that gives you e to the x times y is equal to, oh man, but when we integrate that, what happens? By parts, okay? We've done it before today, haven't we? Let u equal, help me? X, then dv is equal to e to the x dx, then du is equal to dx, and v is equal to e to the x plus c, right? Here we do need a plus c in there. All right? Well, we'll wait and do it later. Okay, then you do your uv. So this integral would be x e to the x minus the bottom line down here, which would be the integral of e to the x dx. Okay, this would be x e to the x minus e to the x plus c. That's where we'll put our plus c. All right. So that's the right-hand side. Here's the left-hand side. So we're going to divide both sides by e to the x. So that'll wipe out that, wipe out this, and put e to the minus x here. So what do we have? Y is equal to x minus 1 plus c e to the minus x. But we know that y at 0 is equal to 4. So this will yield 4 is equal to, when x is 0, you get minus 1 plus, and when x is 0, you get that c, right? So c is equal to 5, right? Okay. So let's go back and plug in. Y is equal to x minus 1 plus 5e to the minus x. There it is. Now, second, is that what they got? Okay. Yeah, y is equal to x plus 1 plus 5e to the minus x. Yeah. Now, something like this when x gets very large, this is going to 0. So you're going to, and for very large x's, you're approaching y is equal to x minus 1, which is this line right here, right? So we call this part the transient part, transient term, because when x is small, that has a great deal of influence. If for c is equal to 5, that's going to be, this is the one that our solution is, okay? other C's greater than 0 are going to be up here, and C's less than 0 are going to be down here, but and C equals 0 would be here, because that would be x minus 1. Okay, that would just be that term here. So we're this term right here. In the long run, it's approaching that x minus 1. But for small values of C of x, then this transient term does have a significant influence. In fact, it dominates near 0. This is just completely left out. But for large values of x, say anything greater than, well, they don't, oh yes, they do, anything greater than 4, that's just basically going to be x minus 1. All right. Does that eat up most of our time? Okay. We got any left? Over. Okay, sorry. Well, not too sorry, but it's okay. We'll pick up next time and just mention the piecewise linear differential equation. That's on the bottom of page 59. Okay. And let me put my mark in there. Ooh, this is a long section. We don't have much more to go. Think you can do any of the odds that are in the back of the book, 1 to 23. And I think you can do any of the odds in the back of the book, 25 to 35. Think you can do either 37 or 39 if they're in the back. And let's hold off on the next part, because that's where your piecewise defined piecewise linear differential equation is. So we'll pick that up next time. All right, good deal. Any questions? Okay. I thought I put it in Blackboard, didn't I? Yeah, I graded it. Yeah. And I can't return it until I see if they've taken Peyton out of the class. If they've taken him out, then I'll return these things. But I won't know. I'll know it fairly soon, because I'll be doing my attendance next. But it's going to take me a little bit to do that. I don't know. They called this morning, so I assume they took him out, but that's an assumption.
Is that engineering one you was talking about earlier, is that on our website? Like on the Lawson website?
I don't know. They used to put, no, yeah, you can for sure. Let me see what this is. Yeah. No, this is the other thing. This is the, yeah. There's a bit of stuff to do for it, so you got a bunch of humping to do to get that done today. Okay, see you on Wednesday.
Well, I think I did see the poets one on here. That's the one that you were talking about, right?
Yeah, that's the one. Yeah, the poets, that's the one.
Okay.
Oh, you've already applied for that?
I haven't yet. I just found out about it what was that, Friday?
Uh-huh.
I was at this thing.
Oh, I see.
So some of this stuff, like I gotta do a crap ton of stuff.
Yeah.
I kind of found out about it at the last minute, so
Right.
I kind of my brain all over the place.
Yeah. The interior of the brochure is basically this page. This here, I can't read enough of it to get anything good out of it. But this part. Yeah. This is the main thing. That may have been on the other thing, too. Yeah. And that shows. Yeah, this is old. So I was going to take that to my office. I've left it up here several days. I'll try to remember to take it out. All right. Oh, I've got to end this.